So to start off, let me just point out that mathematicians get really happy when they can predict something special will happen. Right? So mathematicians are not really all that excited usually about that picture because two lines usually intersect, and they're not usually very excited about that picture either because that's what three lines in the plane usually look like. But if you know that you're going to get a picture that looks like that, mathematicians get happy, right? And so this becomes interesting. So from antiquity, you have theorems like, I don't know, the angle bisectors of a triangle all intersect at a point. And so you get happy because there's going to be that point where they all intersect. So this is sort of the flavor of this talk, is things that happen that are special and how you might predict them. So let's move forward to calculus, and I'll phrase a particular theorem not in its general mathematical statement, but sort of heuristically. And so this theorem says that if you consider the equator on Earth, and you think of a point P on the equator, and then you think of its partner point P prime just on the opposite side, the antipodal point, and you look at the temperature of P and the temperature of P prime, and then you kind of run around the circle, then the theorem is that at some point P on the equator, the temperature at P is equal to the temperature at the antipodal point, the point just on the opposite side. Now, I don't know, does that sound surprising or not surprising? How many people are mildly surprised?
Depends how much experience you've had.
Okay, it depends how much experience you've had. And so that's probably right. So, this is an easy one, and we can prove this. We're going to assume the temperature is a continuous function. It's nice, smoothly varying function. So, we could think about making a graph of the equator, and let's, give ourselves some coordinates, maybe 0 to 2 pi, to go once around. And what am I going to graph? I'm going to graph the temperature at P minus the temperature at P prime. So suppose the temperature at P, T of P minus T of P prime has this value here. Well, then what do I know at pi is the value of this function? It's the negative of it, because now I've switched the role, right? P has cycled around to here, and P prime has run around to here, and so they've traded roles, right? So this is going to be there. So now this was this nice function. So actually, one theorem from calculus tells us that at some point, this difference is equal to 0.
The intermediate value theorem?
The intermediate value theorem, right? You've got a nice continuous function. You've got to get from here to there, and you're not going to manage it unless you go through 0. So it's a nice little result from calculus. And there are similar things that are definitely more sophisticated, but we can actually stay geocentric for a bit. And actually, the whole talk is sort of geocentric, or universe-centric. So now, actually, let's consider another theorem. Again, not phrased so mathematically, but in terms of the globe. And let me look at the whole globe, and I'm going to again consider points P and their partner through to the other side, P prime, just on the opposite side of the globe. And I'm going to consider the temperature and I'm also going to consider maybe the barometric pressure. And so the statement of the theorem is that for some point P, you have that the temperature on either side of the globe is the same, and the barometric pressure also is the same at that point and on the other side. Now, this is actually a pretty sophisticated theorem. So this is the Coulomb theorem. And you can prove it in topology. And I'll just say a few words about an idea of how this can be proved that's maybe a little bit similar in flavor. But the idea is that, again, I'll be looking at the difference in the temperatures and the difference in the barometric pressures. And so half the time this will be positive and half the time it'll be negative, right? Because again, the p's and the p primes switch roles. So as you look around the globe, there's sort of the half the time that it's positive, the half the time that it's negative. And you kind of draw the curves where it divides. Again, by the intermediate value theorem, it's kind of to pass through zero. Likewise for the barometric pressure. And what happens is that you'll have sort of a set of curves that divide for the temperature and a set of curves that divide for the boundary. In some place, those curves are going to have to intersect. And, that makes sense since sort of half of it has to be one and half it has to be the other. They maybe aren't equators, but in some sense, there's going to be a curve that kind of cuts the sphere in half and another one that cuts the sphere in half. So maybe it's not such a surprise that they intersect, and where they intersect, that means this function evaluates to zero and this function evaluates to zero, so I have equality of both temperature and barometric pressure. So now you can rest assured that if you wander around the globe enough, I guess you have to get there at the right time. It's changing, so it's kind of tricky to find the place. But that's what it says. And so, was that one surprising? Sure. Right answer. Okay, so now this is a pretty sophisticated theorem from topology. There's another theorem from topology, which actually you can prove it independently or you can prove it as a consequence of this theorem. And there's a nice paper, and if you are interested in it, I'll tell you where to find it, by Francis Su, that shows how the next theorem follows from this one. But here, I'm going to consider a disk. So this is just x squared plus y squared is less than or equal to 1 in the plane. And I'm going to consider a map from the disk to itself. So this is like a function. It's actually just like a function from R2 to R2. And it's going to take the boundary of the disk to the boundary of the disk. Actually, it's going to... So it is... No, it's not going to do that. It's not going to do anything. That's for later. So it just takes the disk to the disk. Sends point someplace. So you can think of this, one way to think of this is to take, your disk as a piece of paper, pick it up, crumple it, okay? Don't tear it, crumple it, and then just project down and see where everyone went. Okay. You could also map all points of the disk to one point if you want. You can really do anything you want, but the map has to be continuous. And the claim then is that there exists some point x, well, I call it xy since I picked these coordinates, inside the disk such that this map sends the point to itself. This is called a fixed point. Meaning, even though your might have done some crazy stuff when you crumpled up your paper and projected or whatever. There's one point that didn't go anywhere, it just sat there. And this is the Brouwer fixed point. Yeah. So these theorems are from the early 20th century, it's already last century by now. This one I think is from the 1930s. This is from like 19. Where did I have as the date for this? The Brouwer fixed point theorem, 1904, 1909. So really right at the turn of the century. Now you can actually understand, proving things and actually making sure it's really true, and really true also, you can raise the dimension if you want also and have a similar theorem, essentially the same theorem. It gets, again, need some topology to prove this, and it's actually algebraic topology that is the field that sort of knocks this off really well, but we can actually understand the proof, so at least to believe it. Let me say you should stop me if you have a question, because I don't know, what the level of the audience is. I know I have some ringers in the audience, but I may have some people who this is, and I can slow down or speed up as you wish, because the talk is pretty fast. So let's, this is actually going to be a proof by contradiction. A sketch of the proof. And I'm going to suppose that there is no fixed point. Well, that's going to let me consider any point in the disk, and then consider where it got sent, which is not itself, right? That was our assumption. Which means that if I were to stand at this point and then look through where it got sent, I'll pick up some point on the boundary. And I can do this for every point. And you have to argue that do some work to show that this is actually continuous, but it kind of makes sense that nearby points are going to go to nearby points, and so you probably believe that this is continuous, and so you can construct a continuous map from D to its boundary. Come on, if you're going to map the whole disk to the boundary, you would have to tear it someplace. And it's that tearing that would break that continuity, and so you can't do it. And so this is impossible. Because of it, you having done the work to prove that it's a continuous map, and then invoke the algebraic topology to say that you can't map this, you actually can't map this disk, no matter how hard you try, onto its boundary. But for us, we could just sort of say, yeah, we can do that. So these are results that rely on algebraic topology, and the father of algebraic topology is often thought to be, or deemed to be, Henri Poincaré. And so Poincaré, who was working heavily at this time at the turn of the century, had some really interesting work habits. I didn't know that, but look up at that nice biography site at, I think maybe it has moved, but you know what I mean? There's a nice mathematical biography site. It used to be at the University in Scotland. People seen this?
They have mathematician of the week.
They probably do have a mathematician of the week, but almost any mathematical biography, if you're not looking at Wikipedia, you can probably find yourself in their set of biographies. And they're pretty nice biographies, but he was, obviously had great focus because he worked for 4 hours a day. He had a rigid schedule. He worked from 10 to noon, and then from 5 to 7, and then later in the evening he read some mathematics. He also apparently worked from first principles, meaning he didn't sort of bother with how anybody else proved anything. He just worked it up from the ground up for himself. And he also didn't say, oh, over the next 2 years I'm going to sort of head towards this result. He would just sit down with his notebook and start calculating or doing whatever and going wherever it led. Almost sounds like sort of stream of consciousness. But obviously he had a lot inside and some very serious focus. So from here I think I want to, right, so what are some of the things, what is one of the things that Poincaré did was he really started to understand how to study spaces using algebraic techniques, so hence algebraic topology. And so the first thing that he did was Poincaré developed the notion of a fundamental group. And in particular, first at least of a surface. So for instance, just heuristically, it measures the extent to which loops in a space can be contracted to a point. And I'm not going to say anything specific about it, but it's sort of a very flexible notion, but he managed to turn it into, very organized mathematics that you can calculate. But you could imagine some kind of a surface. This is like kind of like a donut with 2 holes. Okay. And if you consider a curve on the surface of this, and remember, this is a surface, you have to not go down inside of it. You have to stay right on the surface. And right on the surface, I can contract this to a point. I can just sort of pull it in to a point. But if I look at a curve like that, I can't, no matter where I went, without breaking. It can't squeeze. So this is something that tells you about this space when you think about the curves on the space. And he was able to show, for instance, that if all loops on a surface that has no boundary so I'm not talking about like a disk, it doesn't have any boundary, and is finite in extent. So I'm not thinking of like an entire plane, although some of these things might certainly make sense to look at as objects. Then the surface is a sphere.
I think there's some bit of the sentence missing here.
Yeah, maybe.
The surface has no boundary, it's finite in extent. What do all loops on it do?
Okay, if all loops, yes, that's
You mean
right.
all loops
So if all
contract
loops
on
on
the-
a surface that has no boundary and contract, yep, there we go. Otherwise, it doesn't make any sense. Extent, contract on a surface, say, let's put a comma there, contract to a point, thanks. Then the surface is a sphere.
So because you have some sort of finite extent, this is done usually in like this is done in R cubed. This is done with Euclidean notion.
I could put it in there, it doesn't need to be, but it can sit in there. This is just to make sure that I'm not, I'm not thinking about, say, so I'm not thinking about, so here is an object that is a space that is finite in extent, let's see. I have to say more. I'm sorry, I'm trying to not say compact. But maybe I better say compact. Has no boundaries, finite in extent.
I'd be willing to settle for bounded. It's not exact, but it gets the idea.
I'm going to put in is compact. So that means, basically, I'm not looking at this kind of an example where I could have a hole where I could have a loop with unsurrounded. So I'm looking at, the family of surfaces that we're looking at that would be candidates are things like a sphere, the surface of a donut, having more than one holes, but also a Klein bottle would be fine. Okay. Other surfaces, so they don't have to be orientable. But this fundamental group is able to detect that this is the sphere. So now this rubs very close to Poincaré's big gift. Okay. Poincaré's big gift is the question up in dimension. You have to sort of, again, I'm not going to talk about it now. If you want to talk about it with myself or any of the other topologists or people in the faculty here about a three-dimensional sphere, which you could imagine as three-dimensional space by adding a point at infinity, kind of wrapping it around, closing it up. And ask if you have a space that is three-dimensional, is compact, has no boundary, and maybe all its loops contract, is it actually the three-sphere?
I think it's probably worth clarification. I mean, people think of a sphere as being 3D normally because it's in 3D space.
That's right.
But only the actual outside of the sphere you can move in 2 dimensions. You mean a sphere the outside of which you can move in 3 dimensions.
So here, this sphere is a two-dimensional sphere.
Okay, that's the...
This is the issue. This is a two-dimensional sphere because on this sphere, well, if you imagine trying to move around on it, or actually think about coordinates, how do we usually measure the position on the globe?
Latitude, longitude.
Latitude and longitude. So there's 2 degrees of freedom. You need just 2 data points, 2 numbers to specify the position. So this may sit naturally in 3 space, but it's a 2-dimensional object. And you can think of it as being related to the plane. If I take out a point, I can kind of unfold it to be the plane. And so likewise, if I had a 3-sphere and I took a point away, I could unfold it and I'd have all of the usual 3 space. So it's a big object that you maybe haven't thought about before. But Poincaré asked if all the loops in it in such a 3-dimensional object contract to a point, is it in fact the simplest 3-dimensional space, a 3-sphere? And that's the Poincaré conjecture, which has been closed only recently and was a huge motivator of mathematics in topology and in geometry also. So the other message here is often the questions that are asked that aren't answered in mathematics that are really drive the subject sometimes more than the answers. So that was a big question. Now, the actual focus for today is another unanswered question of Poincaré's. And so it's related to these fixed point questions that we had before. And so let's just say, Poincaré's, I'll just write it, because Poincaré's big gift, I would say, is the Poincaré conjecture. I mean, he got a lot of big gifts, right? I mean, the fundamental group, a lot, but the question that's the big gift is that one. So a smaller gift is Poincaré's last geometric theorem. And I don't want to go right to stating it. I want to talk about what the object is that we're focusing on first, which is an annulus. So this concerns an annulus. So we're thinking, I want to go back to thinking about fixed points. And imagine, so an annulus is just a washer. So a disk without its center, so this part here. So that's my annulus. And what we're going to do is we're going to consider maps from the annulus to itself. And I'll call it A. Now, this is going to map the boundary to the boundary. And in fact, I want the outside boundary to map to the outside boundary, and the inside boundary to map to the inside boundary. But I want points on the outside, not necessarily to move the same amount to the left or clockwise, counterclockwise, but to all move counterclockwise. They all have to move. And points on the inside all have to move clockwise. That's my stipulation, yeah.
But since you can run around the circle the whole way, how do you tell if something is counterclockwise or clockwise at another point?
Sure. Basically, you probably aren't going to move that much. One way of saying it is that you want it to be, the map to be isotopic to the identity is one helping thing, but then you could make them move a lot, but you're not going to be able to, how shall I say, they can't pass each other, right?
I can go back to that, sure.
They can't pass each other, and in some sense, on average, we don't need them to move a lot. I mean, if they were moving too much, we could just undo, let's say take away a full rotation.
But if you rotated the whole thing by 3 pi over 2.
Yes, that would be the same thing.
Is that same thing as rotating it by minus pi over 2? You rotate it.
Yes.
So which does that count as rotating it
Yeah.
counterclockwise or clockwise?
So there is, let me say precisely what it is, because it has come up. And so, and it is helpful to say precisely what you would do. Okay, so here's the stipulation, and that is that you imagine an infinite strip, and let's put some coordinates on it. Let's imagine that this is, let's give a theta coordinate going around, and a radial coordinate going out, and maybe we'll put this at 1 and put this at 2. And so here I'm going to put, this is the radial coordinate, this is theta, here is sort of a long strip, infinite strip, starting 0 and then 2 pi and so forth. Now, any map of the annulus will be periodic with period 2 pi. What you want to imagine, though, is now, first of all, the relationship between this strip and this annulus is that I'm going to let, it's given by the coordinates, but this means that you have to pick this up. You actually have to flip it because of the way because this is the direction of increase of theta, and this is my outer boundary here, so this has to flip around and go that way. But basically, you just wrap this around and around and around and around and around. Right? And so the condition is that if I look at this map here, just look at how the map, I'll call it phi tilde, then points here have to move which way? That way. And points here have to move that way. That is precise.
Okay.
Okay? So it's a very good question. So this is the scenario. So the question is, for such a map, does there need to be a fixed point? And let me say to the people who know what I'm doing, I have not put all the hypotheses on yet. I just want to think about this map, with just this much hypothesis. So do you think there needs to be a fixed point? So I pick things up and I have to sort of scrunch this again. You can think of it as scrunching it around or moving points however you want, but points here have to move this way, points here have to move this way, and then they'll project back down. do you think there has to be a fixed point? I think we needed some voting. So, must there be a fixed point? And you have to vote.
No, it's.
So this is yes, and this is no. So how many for yes? Ooh, lots. Okay. That was the winner. Were there any no's? All right, so we got like 6 no's.
6 units.
Okay, so let me say it's hard to think about maps as just as such. So let me restrict the question actually a little bit and think about some special kinds of maps. And so think about maps that are the result of the flow of a vector field. So for instance, first let's make sure we understand what happens with this kind of thing. So suppose, just to make sure we understand. So for example, I might have a vector field that looks like this. I've got a dot, I've got some little arrows that are going out, and then I have some other arrows that are maybe kind of going outward, but they're kind of cycling a little bit counterclockwise. And then you go out a little more, and they're really just going around in a circle. So what this means here, or what I mean for this flow is, okay, well, now these are just telling you if you're standing at this point, how fast you're supposed to move and in what direction. Okay? So we turn on time and we let ourselves flow. Okay? And if we flow for a little bit, how would you describe how the points move? Well, this one does what? Just sits there. That one just sits there. What happens to, a point here? It goes out, right? Okay. And another point here, depending on how long we run the time, might go out and around a bit, yeah? And if I let time run for a long time, where are points going to tend to go? Out, they're going to kind of spread out towards the boundary, kind of like a centrifuge, right? They're going to kind of get pushed out to the outside. Right? Okay, so now I can choose how long I want to let my time go, but whenever I stop time, I say, oh, stop, wherever you are, that's your map, okay? It was where you were, and then it was where you are. So that's a map defined by the flow. So now let's try and do this for this vector. We're going to consider a vector field on the angles. But now it sort of makes sense with these arrows because, clearly we've got to have some kind of arrows on the boundary that are going to define how things float on the boundary. And likewise here. And so now the question is, well, that's what a fixed point looks like. It looks like a dot, right? Can you fill this in with arrows so that they vary smooth, nicely, continuously, okay? No big jumps. So that the arrows go counterclockwise on the outside, clockwise on the inside, but there's no dots. Do you think you could do that?
So let me see if I understand what we're saying. So we want to sort of, for each point, we want to say that the vector states how far in rotating in that direction that point has been moved.
So, I'm not sure I understood your words, but let's see. The map, so I will have a sort of a whole, once I've filled this in with arrows, to get the map I would turn on time, let things flow according to the arrows,
Where did these arrows come from? I guess is what I'm asking.
Well, okay, so I'm getting to dictate them. So here I gave them to you,
Okay.
okay? And then we had a flow that you understood.
Mm-hmm.
Okay. So now, this problem, however you put your arrows down, we can turn on the flow and then stop it and get a map. So now my question is, so here, if I don't have to, let's say, suppose, let's do another example. Suppose I had the sphere, then there's a pretty natural kind of a flow, which is just you let all the points kind of flow downwards from the North Pole to the South Pole. And that has two fixed points. The North Pole didn't go anywhere, and the South Pole didn't go anywhere. And actually, you can't fill this up with arrows or vectors without a point. That's another fixed point theorem. This is, you can't comb a hairy ball theorem. But I want to stick here and think about,
I think I'm going to vote yes. I think we can prove that there are fixed points there.
okay. So the answer is no.
All right.
Which means these guys were the winners, because not only among all maps could we do it, but we can even do it with these guys. Now, we've got some radial symmetry here. So, angular symmetry here. So let me think just about on this line here, how to make the arrows go. Can you, on this line, get a family of arrows that varies from here to here without making a dot? Turn them around, right? So I could do that everywhere, on every radial segment. And in fact, that's why I could, in fact, get all the, so in fact, I can make a map, because in fact, I can make a flow, and we can think about what that flow would be. But what does that flow do?
It's like it pushes points towards the inner ring.
It pushes points towards the inner ring, right?
Kind of like that.
The ones on the outer ring, they just go like out on the outer ring. But if you're not on the outer ring, you kind of start getting pulled in towards the inner ring, right? Okay. And as you do that, you get turned around, right? Actually, so if you let time run for a while, for long enough, you'll end up going like that. Okay, so there was no fixed point. That's fine. I wanted to make sure that we understood that before we say the theorem, because otherwise the theorem doesn't look very interesting. So now you said something interesting, and that was that these points that are out towards the outer part have to get pulled towards the inner part. So in particular, this outer layer here, or this outer half, I guess. Maybe I don't want that. Minus this, minus the boundary, is going to have to get pulled in. And maybe you can start to believe that actually what this is doing is compressing things. If you thought about some sort of, something swirling in towards it, you would actually be expecting to have some kind of a drain, right? It's kind of pulling, and if you didn't have a drain, I don't know, incompressible fluids can't do this because they can't sort of squish up, but you would be trying to squish things in on this inner ring, right? Okay. So that's not what Poincaré's last theorem is about. Poincaré's last geometric theorem adds a stipulation.
So water could not do this, you're saying?
So water can't do this. Water
can't
is
flow
generally
up there.
incompressible. So water can't do that. So suppose also P preserves area. Well, now we can't do that. No. Can't happen. And Poincaré's last geometric theorem says that then there are at least two fixed points. Now this doesn't look very interesting if you didn't understand already that without the assumption about the area, you didn't have to have it. Okay? So without this assumption, we certainly, even with a flow, could get no fixed points. Yes.
What do you mean by that the map preserves the area?
Right. So we have to say what that means. So that's like so you can think of it like an incompressible fluid. Okay. So suppose you had a dish or something with some fluid, and so it's essentially two-dimensional, and you could swirl it around, but the fluid can't. You can't take a patch of fluid like this and have it move around and occupy just this much space. Okay. So any little bit of fluid that you would look at, wherever it would travel, it might take up a different shape of space, but it's going to have the same area.
So if you take any closed region and consider what phi does to all of its points,
That's
you'll
right.
get a different curve, but that different curve will have the same area.
It will contain the same area inside. That's
Okay.
right. Everywhere, always. Okay. So that's what area preserving means. Great. So now the other thing we kind of encountered was, I don't know about you, but I think it's harder to think about like all maps than to think about maps that come from a flow. Okay. So the proofs for this, for Poincaré's last geometric theorem, he didn't prove it, but a year later, Birkhoff did prove it. We proved at least that there was one fixed point. There were some problems with how he got the second fixed point, and there have been other proofs since then. They really take some work. But we're going to consider the simpler problem. We'll simplify it a little bit. And we'll also suppose the map is the result of a flow. Or a vector field. But now I need it to be area preserving. So let's think of a nice area preserving map, and not worry about having fixed points. Maybe we can even have a lot of them. Let's just worry about getting an area preserving map. Okay. So let's take the annulus, and how could I put down vectors so that I would have a flow that I would know was area preserving? And I'm not going to worry about how many fixed points I have. If you want lots, that's fine.
I have one idea.
Yeah.
Make it so that every point only rotates radially and never moves in or out.
Rotates along the angles,
the
right.
points that are closer to the inner rim will rotate faster in a clockwise direction. The points closer to the outer rim go faster counterclockwise. And smack in the middle between the inner and outer, every point is completely stationary.
You like it? Area preserving map. Turn the time on. These points all sit still. One's outside, move counterclockwise. One's inside, move clockwise. Faster on the further are you away.
Do people really believe it preserves area?
I suspect so, but I'm not sure.
Yeah, it's like a rectangle and a parallelogram are in the same area because they have the same height, right? Sheer.
Or if you looked at any shape that wasn't, any shape that's in one of the specific sets, it's going to stay the same. So you have two sets that preserve area.
Well, the idea was what would happen to a little square like this, right? Its outer part would move out faster than its inner part, right?
Yeah,
So
but I feel like if each radial slice has a certain amount of length, the slices, each of the individual slices of the same length, whether or not they get really stretched out and sheared.
You could also just throw in the fact that it's speeding up and just make it all constant.
Right, so this is the calculus way of thinking about it, right? You think about it like a whole lot of baklava, right? On all those little line segments, and they all moved over, right? And they all rotated, and however much they rotated, yeah, whatever. But they all stacked up to give you the same if you thought of it like a Riemann sum.
Yeah, that was basically it.
Good. So that's good. So we've got an area of preserving that. And we got lots of fixed points, but sometimes you just kind of like kick it, perturb the flow a little bit, and maybe we can destroy them. Right? So maybe we can make them go away. But it's still sort of hard to think about what we might get and how to preserve it, how to ensure that it is area preserving. And so we're going to restrict again to a certain class of vector fields. So suppose further, so we just keep simplifying the problem. The problem's too hard, just keep simplifying the problem. So suppose further that the vector field comes from a function. And I'll tell you how. I know it seems a little bit mysterious, but so I'm going to take this vector field, and at any point in the plane, so I have a function from, let's say this is sitting inside of R2. So I have a function from the annulus to R. And, well, it's a function, this is sitting inside of R2. So I can take partial derivatives, and this is kind of a strange thing, but I'm going to take the negative of the partial derivative with respect to y, and then the partial derivative with respect to x. If you like, this is equal to, it's related to the gradient by this matrix. So this is, if you know about the gradient is just the more natural vector coming from the partial derivatives. So differentiate this function of two variables with respect to x and with respect to y, and hit it with this matrix, and it spits up into the first entry the negative of the first derivative with respect to y, and this may say, I don't see why I would do this.
Rotation?
Well, it depends on the function.
No, the matrix, 0 minus 1.
Oh, yes, that is a rotation. Absolutely, yes. In fact, it's wonderfully a rotation by 90 degrees. Or, if you like, it's actually multiplication by I if you want to think of the plane as a complex line. Okay, where is the complex? It has complex numbers. All right, so why is this good? Well, this is good because theorem, any such vector field is area preserving. And, we don't have a lot of time, and I don't want to keep you here all evening, so I'm going to appeal, I think, to a little bit of multivariable calculus. But do people know how to ensure that if I have a vector field, V, which has components, I don't know, little u and little v, that it is actually area preserving?
Divergence is 0.
The divergence is 0, right? So, so this is area preserving. If you don't know what this is, that's okay. This will be just something with, some partial derivatives. Is area preserving if its divergence is 0, meaning what? How do you calculate the divergence? Anybody know?
It's a sort of like a cross product.
That's a curl. Curl's the one.
This was the 13500 homework I didn't turn in.
Assuming I have it in here. Yeah, well, divergence of the vector f dv, but I mean,
But do you have a formula for the divergence?
like, what do you mean by like the actual thing of it? Like, d del f over del x plus del f
Isn't
over
it
del
the
y?
null operator dot the function?
Yeah, so I think all I have to do is differentiate this first component, right? And add it to the second component?
Yeah.
Okay, so that's on the partials? And so all
Which
this
is
is
what
equals
he
to
said.
0? Is that correct? That look good?
Which is what he said. Dot
Yeah.
the map line.
Good, okay. So let's try that out here. In our case, that would mean I would take the partial derivative of this with respect to x and add it to the partial derivative of this with respect to y. But what do you know about functions? Doesn't matter what order you do the partial derivatives, they're equal, right? So this is 0, and so we're happy. What? So we now this is really cool because now what you have, functions are easier, right? This is good, functions are easier. So I have a way of generating area preserving maps by thinking of a function, okay? And then writing down a vector field that comes from it. This is just these partial derivatives. Furthermore, tell me your name.
Michael.
Thanks to Michael's observation, this is a gradient vector field. A gradient vector field means you just like point in the uphill direction. Okay? So for your function, how to go, what you stand, you have a function on R2, and you want to know, say, the temperature. Okay? And maybe it's the temperature function. You go, I want to go wherever it's hotter. It's hotter over there, so my vector points this way. Okay? And what do you do with that gradient vector field? You hit it with this matrix which says, turn 90 degrees. Okay? And we'll get an area preserving now. So let's see how this goes. In fact, the vector field that was suggested on the annulus was something exactly like that. The vector field that rotates, maybe not the exact one, but the vector field that rotates things around comes, let's just look at a gradient vector field for a particular function. So let's take a function on the annulus. I guess I need to go into 3D here. So here's my annulus sitting in a plane, and this is maybe a z-axis here. And so I need a graph of this function. I'm going to graph this function, and it's just going to be a nice, simple graph. So when I stand here, this is the height of, this is the value of the function. Where should I go in order to get to a higher value of the function? I should go out, right? Outward, because that will take me up to a higher level, right? So the gradient vector field for that function, everything would go out. But now, so that's a gradient vector field. But now we said to everybody, turn, like you're multiplying by I, turn 90 degrees counterclockwise. What do we get? We get cycling around. So multiply by 0, minus 1, 1, 0, or rotate, and you will get a vector field where everybody is going around. Not area preserving, area preserving. Great. So now I'm not going to prove Poincaré's last geometric theorem for maps or for flows, but I'm going to, or area preserving flows, but I'm going to look at the ones that come from functions. So now I need let's try and look at what happens, and let's take our original example of a flow. Let's see, so we've got to have some kind of this is our annulus. I'm again going to think of this in an xy plane. Let's see. So x, y, and then I can graph a function z. And I think that imagine a graph that kind of looks like this spun around. Okay, so take this little hanger-like thing and spin it around so this is its top. Well, then what's the gradient at points that sit down here? Well, that means you're already at the top, right? So that means your gradient is 0 because you don't need to go anywhere. You're already there. In fact, you're there all around. So there are our fixed points, right? And if you think about it, well, to go up here, you should go, I don't know if I've got my directions right, but here you go in this way, here you go in this way, and then we turn 90 degrees around, and I don't know if I switched the directions, but one boundary will cycle one way, one boundary will cycle the other way. Great. Now we want to destroy all those fixed points, right? Well, how many can we destroy? Well, we can come along and we can smush this down. You can say, that was sort of silly. Let me make, this one around here lower and let that top part kind of, cycle around. So that means that now above this point, I definitely had a non-zero gradient. I should have, if I wanted to go up, I would go out over around this way, right? But I still have, on the annulus, I have a function. Do I have to have a maximum? Yeah, I have to have a maximum, right? And do I have to have a minimum? Yeah. And so at the maximum and the minimum, the gradient will be 0.
I'm suspicious about minimum. Do you mean on the whole 2 circles? Is that what you mean by minimum?
Yeah, so right here at this, I'll have a critical point at this saddle point here. So, no, I guess it's not a minimum. It's not a minimum, right? It's not, these are the minimum, but I have the minimum, okay, you're right. The minima are, thank you, the minima are down here. Okay. But in this example, you can see that I can't get away without having a minimum on this circle, right, which will give me a saddle point, at which if I stand right there, then because the derivatives are actually equal to 0 there, I will get a 0 gradient. So I'll get a fixed point here and a fixed point there. And so those are the 2 fixed points that Poincaré would want me to find. Now, this is sort of the beginnings. I mean, Poincaré is sort of seen as being the father of algebraic topology. This theorem about the fixed points on the annulus is seen as the sort of beginning of symplectic topology. So this is a much more modern field that didn't really even come into existence until the 1960s, when Arnold conjectured that, well, if you look at this condition of area preserving, let me say the reason this area preserving came up was because Poincaré was thinking about celestial mechanics, and he was thinking about the 3-body problem. So you have 3 objects in space, 3 planets, and you're trying to understand how, whether there are any periodic orbits. And, you know, so you let these bodies sort of, their gravitational fields interact, and you have some initial conditions, and you want to know whether you can assure some periodic orbits. And what he was working on was he showed that if you have fixed points in this map here, that he could produce periodic orbits. And the area preserving this comes from the mechanics. It comes from the fact that he's working in phase space where you're looking at position and velocity together. And Arnold asked a much more general question about spaces that kind of are like phase space but are more abstract. And he conjectured that, you know what, you get a lot of fixed points. You get a lot more fixed points than you would think you would have. And in fact, if you think about flows that come from vector fields that are not just like this, that come from a function, maybe you let that maybe you want to mix it up a little more and let those functions change over time. Okay, so your vector field can change as you go. That you still get as many fixed points as if you just had a function, one function, without changing it. And so this was the beginning of, and it was a surprise. There are a lot more fixed points than what you had thought. And that was the Arnold conjecture, and it, you know, again, gave birth to lots of mathematics. So.